Hello students, welcome to our next lecture. Uh, in last lecture, we had started our discussion once again in process management, where we had picked what is program and what is process. Then we moved into PCB and we were discussing about process state transition diagram. So in this one, what we had done, that we had picked that there are two basic models. First one which we had picked, that is two-state model. Now this is having two states. One is not running and the one is running. Running means it's running into the CPU, and not running means due to any other reason the process is in not running state. And we have picked that there are certain restrictions with respect to two-state model, and those are that how to identify that which process is not running and what is reason behind it. So there is a pool of processes having several different reasons of not running, and all are in single state. So to distinguish between processes is not feasible in these two state models. So hence we moved into the new set of model, which is a five state model. In five state model, what we had done, we had picked that each uh, thing further, that we had picked that not running is get divided as per the functioning. And we had picked that at the start, what it will happen, the process is in new state. When it is in new state, that when you click any process, it is in new state, means that process is newly created and it is going to be loaded into the memory. When the process is loaded into the memory, then it is ready for execution. After process is in ready state, then what it will do, it will move for the running. So now once process is running, in which it is running, it's running into the CPU. When process is running, it is in running state. Now after running, there are two possibilities. One is that process will get terminated, or another one is that process will move for waiting state. Now termination is quite known thing, that process has completed its task. And waiting means that due to certain reason process wants to wait for some other thing. For example, certain IO event occur, process wants to display certain things. So what it will do, or process wants to read certain new data, so it will wait for the further instruction. Hence it is in waiting state. Now from waiting, what will happen, that it will move into the, once again, ready state. Now this was the discussion which we had done so far. So there was one question, that why we are having these arrows, and we had left that thing with one simple thing, that can we move into different one. So before I'll move into the further sixth state, I'm going to pick or complete diagram, where I had picked that I am moving into the new state. From new state, my process will move into the ready state. From ready state, process is moving into the running state. From running, it got terminated, or it will move for waiting state. Now from waiting, we had moved our arrow into the running state. Now the question was that there are two arrows. One, do we have or do we require this arrow? Second one, can we have arrow here? So the both things, these are the questions. So the question is that can we have this thing? So let's pick one by one, that can we move directly from running to ready state? Now the thing is, yes, we can move process from running to ready state. The reason is that it's not necessary that each and every time process would like to wait. There is a possibility that certain interrupt occur which is non-maskable, then process wants to move from running to ready directly because the system has forcefully taken the CPU from the process. Hence, it should be sent to the ready state, and whenever CPU is free, it should be given immediately to that process. So hence, we got the answer, the yes, it is right. Now the next thing is that can we have waiting to run? Is it right one? So the answer is no. You cannot move from wait to directly run. Now, what is reason behind it? The reason is that if you will send process from wait to run and process is again coming from ready to run, then both processes will collide here and our CPU will not perform anything. Hence, my CPU is busy without work. It is somewhat that it is overwritten. Earlier, it was happened in printers that if suppose uh, in network printer, two persons has given the command at the same time. So what it will do? The printer will print certain overwritten things which have no meaning for either person A or person B. So that was the thing, that you cannot send process from waiting to run, otherwise there is a possibility that it will collapse with the process which is already running in run state or in CPU or sent from the ready one. Now there is one more argument for that, that somebody tells you that what I'll do, I'll wait for certain time until my CPU is free. Now at that point of time I can send it. So is it the right thing? Once again the answer is no, because there is one possibility. The thing is that suppose at 10 a.m. Uh, from waiting you want to send to the running. Now there is a possibility that at the same time process will be sent from ready to running. Means the time is same, hence the system will not be able to distinguish that which one is earlier and which one is later. So both will get collapsed. So these are problems of synchronization. Hence, you cannot or you don't want to send that thing. Now the other thing is that what I'll do, I'll take one monitor here and this will monitor that who is coming and it will arrange accordingly. So in this way, I can manage this arrow. So the answer is again, yes, you can do it, but it will overload the system. Hence, it is not possible. So overall, what we had done that yes, we have certain arrows, but all arrows are fixed. So this is the 5-state transition diagram where I had picked the all arrows, that why we have certain arrows and why we do not have any other arrow. Now, in this 5-state model, have we represented each and everything or is it sufficient? So the answer again becomes no. Now, why it is no? The reason is that suppose now everything here, everything is in terms of RAM, random access memory. The ready state is in RAM, waiting is again in RAM, the process is waiting in RAM. So what happened that there is a possibility that after certain time, suppose my RAM becomes full. So what will happen? Then due to overflow, there is a possibility that so many of my processes will get overflowed and they will not be returned back. Now suppose one process has completed its maximum task. So it just wants to terminate and suddenly due to overflow, it got out from the memory and it will never come back and it have to again do the same work from zero. Hence, we have another state that is known as suspended state. Please be careful. This is one waiting state. In few books, it is known as blocked state. And this is suspended state. Suspended state is in hard disk. And it says that if your waiting state is having so many processes, then what you can do, you can send some of the processes, suppose all those processes which are busy in IO and they are not currently performing any CPU, then why you are storing those processes into RAM? Instead of that, send those processes into the suspended state and free your RAM for all other processes who wants to run into the CPU. Then once they will complete the IO, what will happen? That from the suspended state, you can move processes again into the RAM, which is in the same state, waiting state. And they will say that I have completed my task and now I don't want to be suspended. I want to return back to the ready. So please bring me back into the waiting state. And it will again send those processes who are currently running for any specific IO or any other thing which is not belonging to the CPU. So that is the reason that why we have the next state in our system, that is sixth state. So this is our sixth state transition diagram. If I'll move back, let's see which state I have incorporated, that is suspended state. Suspended state says that process is suspended from waiting state due to memory overflow. When my memory got full, I'll suspend the process from memory and from waiting state and send that process into the suspended state. And when my memory get little bit free, what I'll do, I'll bring those processes who had completed their IO out of all those processes which I had sent into the suspended state and bring those processes into my again memory. So be careful. This new is in hard disk. This running state is in CPU. Then waiting and ready state are in RAM. Terminated, definitely your process itself got terminated. So this is only representation of completion of the task, and suspended again in hard disk. So new and suspended are in hard disk. So that is overall six state model. Questions about five state model, questions about six state model. So in today's lecture we had covered all those stuff. Now further, once again the question arises that do we require more states? So search for that thing, think about that thing, that We had started with two-state model, pegged running, not running, then moved into five-state model where we had divided my not running into multiple state, which becomes a new state. Process got created, send it to the ready state. Then from the ready state, you will select certain process and send it for execution in running state. Then from running state, it will either get terminated from terminated state or it will move into the waiting state. From waiting state, it will move to the ready state after completion of its task. Then the sixth state tells that if my memory get overflow, what I'll do, I'll send certain processes which are waiting in my memory out from the memory into another state, that is the suspended state. And whenever my memory gets free, I'll bring back those processes again into my memory. So we had covered the memory restrictions, we had covered the operational things. So once again the question is, do we require more state? So students, think for it, and in next class we will again discuss about it, that do we now require more things or is it sufficient for it? So I think that is all for today. In next lecture we will start from the same point. Thank you.